Good morning, and welcome to this online lecture series on uh, multivariable calculus. Okay, and the goal of this lecture series is to develop several variable calculus for Rn, and the details of this course you can find in my web page. Okay, so here you can really find, and you can see the syllabus here and references here. I will mostly follow Rodin principles of mathematical analysis, and I will also post assignments here. Okay, so the thing is, okay, so all of you know that the calculus on real variables. So we will develop calculus on Rn, and so the thing is on real variables. So you have learned about differentiation and integration, and we will develop these notions on Rn. So on differential calculus on R, so on differentiation, you know that there is a theorem called mean value theorem. There is an important theorem called mean value theorem. And on integration, so we have this fundamental theorem calculus. Theorem of calculus. So the thing is, this is on R. Okay. On Rn, actually, there are two important theorems. One is called inverse function. We will study something called inverse function theorem. And another important theorem is implicit function theorem. Similarly, there is another one more theorem which is called so on Rn, actually this fundamental theorem of calculus will generalize to something called Stokes theorem. Okay, we will study these theorems mainly. Okay, so let us begin then. Just wait 1 second. I will drink a little water. Okay, so let us begin with a definition. So I will use this acronym VS for vector space. Similarly, okay, I will use this acronym VS for vector space, and we will be considering only vector space over R. So definition. So let V be a VS over R. VS stands for vector space. Function from B minus 0 to R is called a homogeneous function of degree k if is f of kx, okay, oh sorry, f of rx is equal to r to the power k fx, where x belongs to b minus 0 and r belongs to r. Oh, r greater than 0, sorry. Okay, so let B be a vector space over R. A function f from B minus 0 to R is called a homogeneous function of degree k if f of Rx is equal to R to the power k fx. This will be true for all x belongs to B minus 0 and for all R greater than 0. Here k is a real number. K is a real number. K belongs to R. K can be also negative, positive. Okay. Okay. So observation, simple observation, you can take it outside. So let f be a homogeneous function of degree k, and suppose g be a homogeneous function, g be a homogeneous function of degree say L. Then first observation is if you look at the product of this function f and g, then the function, then uh, the function checks which is nothing but okay, the function f dot g, okay, is a homogeneous function of degree k plus L. Okay. Now the thing is, what is f dot g function? This is the multiplication function. So f dot g x is defined as really, this is defined as like fx and gx. This you can easily check this thing. The thing is, okay, so in mathematics, whenever you write this semicolon and the colon and equality, that means you are really, this symbol is used when you define new thing. Second thing is the function f by g is a homogeneous function of degree k minus L. Okay. So what is the definition of f by g? F by g x is by definition fx by gx. Of course, you have to assume this fact that here we will assume this first. So assumption, the function g is not 0. It is not equal to 0 for every x belongs to b minus 0. Okay. So what did you do first? What did you do? So we define homogeneous function of degree k. Okay. So the function f from b minus 0 to r is called a homogeneous function of degree k if f of rx is equal to r to the power k into fx. And then we remark that if f is homogeneous of degree k and g is a homogeneous of degree l, then the function multiplication of f and g is also an homogeneous function of degree k plus l. Similarly, f by g is also a homogeneous function of degree k minus l. Now, Okay, so okay. So now we want to define something called norm on a vector space. Okay, definition. So let P be a vector space over R. Oh, sorry. Definition. So let P be a Vs over R. Remember this Vs is the acronym for vector space. So Vs is the acronym. A norm, a norm. Okay. So this is the symbol for norm. A norm on V is a function. So this is the symbol for norm. The function from V to R is a function from V to R satisfying the following. So property one, what is the property one? Property one says that norm x is equal to greater than 0, greater than equal to, greater than equal to 0 for every x belongs to B. The second property is norm x is equal to 0 if and only if x is equal to 0. Third thing is, so R norm of Rx is equal to modulus of R norm x. Fourth property is norm of x plus y is less than equal to norm x plus norm y. So this property one is called positivity. Positivity. And second property is called definiteness. And these two properties are combinedly, people say that norm is positive definite. Okay. And okay, so this is okay. So this happens for all x belongs to B, for all x y belongs to B. So the third property is called homogeneity. And the fourth property is triangular inequality. So the thing is, so a norm on B is a function from B to R, which is positive definite, and this is homogeneous, and it satisfies also triangle inequality. So property theme 3 says that norm is a homogeneous function of degree 1. So remark. So property 3 above remark. Property, okay, sorry. Property 3 above says that norm is homogeneous. Norm is a homogeneous function of degree 1. Okay, so this is clear, I think. Okay, so now given any non-linear space, one can define a distance on that space. And so any non-linear space is really um, is a matrix space. Okay, so we will see that thing in later. So okay, so definition. So a vector space V equipped with so it's a norm. So this is called a norm linear space. Normed linear space. So for the non-linear space, I will use the abbreviation NLS. So NLS is for non-linear space. So NLS is the shorthand notation for norm linear space. Okay. Now, so any norm linear space, okay, NLS B, say B, no, this is the norm, can be given a metric space structure. So in particular, it is a topological structure. And what is the distance? So d of xy will be defined by this thing. So here, this is the distance between. To be okay. So this is the thing. Now let b okay. This b comma this norm be a norm linear space. So the thing is, so it has a metric space structure. So you can talk about open set, so closed set and compact set, connected set. You can talk about continuous function on the vector space B. Okay. So let B come. This is B be a non-linear space. This means this symbol means this is the norm on B. So let this is the definition. Let B x comma R. This is really x belongs to B. Sorry, this is y belongs to B. So the distance between y comma x less than R. So this is equal to y belongs to B. So the distance, sorry, norm of x minus y is less than R. Okay. So this is called open ball with radius R and center at x. Similarly, this is this SXR is denotes the sphere of radius R with center at x. So this is y belongs to B, so that distance of y and x is equal to R. So this is really I belongs to B, so that norm of x minus y is equal to R. Yes, so this is P sphere of radius R with center at x. Okay, so you define open ball and sphere of radius R center at x. Okay, so here is an exercise. So, so true exercise. So exercise. So exercise, right? So let B be a normal space. Okay, so okay, so not let us not give it. Okay. So let B be a normal space. Normal space with norm. Now from triangle inequality we have to get. You will get this thing x plus x y plus x minus y norm is less than or equal to y norm plus x minus y. Okay. Okay. So that will give you, so this will give you, this is really x now. So what I'm getting, this is really norm x minus norm y is less than or equal to norm x. So this will give you this. So I am getting this norm x minus norm y, norm x minus. I can change the role of x and y. So I am changing the role of x and y. We get norm y minus norm x is less than or equal to y minus x norm. And this y minus x norm is same thing as x minus y norm. So thus from this, the star and double star, so we get this thing. Norm x minus norm y mod less than or equal to x minus y. Okay. Now call this thing is, and this happens for every x, y belongs to B. Okay. Okay. So what I'm getting, modulus of norm x minus norm y less than or equal to norm x minus y for all x to B. Okay. So the thing is, what, so if, so if, okay, so let us call this as A. So if fx is equal to norm x, then from the A says that from A, we get this thing that fx minus fy norm is less than or equal to fx minus y norm, and for all x, y belongs to B. Now I am calling this as B. If fx is equal to norm x, from A we get this mod of fx minus mod of fy is less than or equal to x minus y. So you know that B is really a metric space. So you can talk about continuous function. So so remark, so remark. So from B, it is clear that the function x going to norm x is continuous on B. Okay. Okay. Now let us give an exercise, simple exercise. So let this be a non-linear space. NLS stands for non-linear space. So first exercise is the addition map is x comma y coming to x plus y. Okay, it's continuous from b cross b to b. The second thing is the map, the scalar multiplication map. Alpha x going to alpha comma x is a continuous map from R cross B to B. So I have two exercises for you. So first exercise says that the addition map from which sends x comma y to x plus y is a continuous map from B cross B to B. And the scalar multiplication map alpha comma x going to alpha x is a continuous map from R cross B to B. Okay. Okay. Okay, so the thing is, okay, so okay, so I hope you will be able to solve this. Okay? So now let us give some example. So let first example, let I consider this space Rn. Okay. Now I fix okay. So I take okay, fix a P with I take a P with 1 less than equal to P less than infinity. Okay. Okay. So the thing is for 1 less than equal to P less than infinitive. Okay, so I fix a P with less than. So let x is equal to really x1 to xn belongs to Rn. So I define this norm xp really mod of x1 to the power p plus x2 to the power p plus xn to the power p to the power 1 by p if 1 less than equal to p less than infinitive. Okay, or I define this x infinitive by this is maximum of 1 less than equal to I less than into n norm of xi. Okay, okay. Now the thing is, X, and this is called LP norm of X. This is called LP norm or L infinity on of X. It's a little LP norm of X. Okay. Okay, so this is called little LP norm of X. So one exercise, one can check that. So exercise, just check that this defines a norm on R. This LP norm defines a norm on R. Okay. And the usual topology of Rn, which you have seen, that comes from L to norm. So the usual topology of Rn, which you are really familiar, that come. So usual topology of Rn, which you are familiar, comes from this thing. So my L to norm. And this L to norm, actually, this is induced from a inner product, and induced from an inner product. And so what is the inner product? This is the inner product. XY, norm of XY is really A is equal to 1 to n summation x. Okay. So for that reason, so there, so you know this Cauchy square is inequality, right? On Rn. Okay. So on Rn, you have this Cauchy square inequality. So that says that inner product of x and y is less than norm x2 y2. This is for all x comma y belongs to Rn. You can take this as an exercise. Okay. 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 So now another definition. So another okay, so let norm A and norm B be two norms on B. We say that norm A is equivalent to norm B. Equivalent to norm B. So, and we will write like this thing that norm A is equivalent to norm B. If so, we will write that norm A tilde norm B if there. So if there exist constant C1 greater than 0 and C2 greater than 0, so that C1 norm XA is less than equal to norm XB less than C2 norm XA for all X belongs to B. Yeah. So let norm A and norm B be two norms on B. We say that norm A is equivalent to norm B, and we will write like this: if there exists constant C1 greater than 0, C2 greater than 0, so that's C1 norm XA less than norm XB, C2 norm X, and this will happen for all X. Okay, okay. Observation. Now, easy observation is something like this. So first observation is norm A is always equivalent to norm A. So, okay, if in that case C1 and C2 will be 1 and everything will be equal. Okay. First observation is this: norm A is equal to. Second thing is, if norm A is equivalent to norm B, and this will imply that norm B is equivalent to norm A. Third thing is, norm A is equivalent to norm B, and norm B is equivalent to norm C. So that will imply that norm A is equivalent to norm C. So this says that, if norm A is equivalent to norm B and norm B is equivalent to norm C, then norm A is equivalent to norm C. This says that equivalence of norms is a transitive relation. And this is really, this says that this is reflexive. Oh, this is symmetric. Equivalence norms is a symmetric relation. This is really reflexive. So that equivalence of real norms is a equivalence relation. Is an equivalence relation. Okay, so remember this thing: if norm A is equivalent to norm B and norm B is equivalent to norm C, then norm A is equivalent to norm. Okay, okay. So now the thing is, okay, so suppose norm A is equivalent to norm B, and this B, both are norms on this on vector space B. Okay, so this B norm A is equivalent to B norm B. These are norm. So this has a topology on. So this will induce a topology on B, and it will induce a topology. So it turns out that if two norms are equivalent, okay. So the thing is, open set here, whatever open set and with respect to norm A topology will be same as open set here with in the topology from B. Similarly, closed set here will be same thing as closed set here. So compact set, connected set, whatever topological property here, it will be same. Here it will be composite. Now the thing is, okay. Suppose X comma D is a matrix space. Okay, so this, so this if So XD is a matrix space. This is a matrix space. Matrix space. So if x comma, so if norm R is equivalent, so if f is a continuous function from x comma d to say v with respect to norm A, so this is continuous. This will imply that f from x comma d to, so it is continuous in this topology if and only if this is a topology are the same. Okay, so similarly, it will happen that if f from this p norm A to x comma d is continuous, this will imply that if p norm b to x comma d is continuous. So this is an inverse attempt. Okay, so and another thing is if with respect to this norm, this if this norm is complete, then this will complete. Means yeah, recall that a matrix space is called complete if the Cauchy sequence in that matrix space converges. Okay. Okay. So another definition. A normal space which is complete is called a Banach space. A Banach space. Okay. Now, an example. Okay, so the thing is, so you consider this space Rn. Okay, so on Rn we have this LP null. Okay, so fix 1 less than p less than q less than infinity. Okay, so so the thing is, if you look at x, so x is a x1, x2. Okay. Now each xi null will always less than equal to norm xp. Okay, so each coordinate modulus of xi is less. So this will give you, yeah, so this thing will be give you norm of xi to the power q. Okay, is okay. So let us not tell. Okay, so this will give you so maximum of 1 less than equal to I less than equal to n. Norm of xi is less than. So this will give you that, and this is nothing but norm. The left hand side is nothing but norm x infinity. So norm x infinity is less than. From here, actually, you will get this thing. Norm xi to the power. Okay. Q is norm q for 1 less than equal to q less than. Okay. Now what is norm xq? Norm xq is really nothing but summation I is equal to 1 to n norm of psi q to the power 1 by q. And see, this normal mod of xi q is less than norm of xpq. So I can put that thing. So this will be less than equal to I is equal to 1 to n is norm of xp q to the power 1 by q. So from here you will get this thing. Norm of xq is less than equal to n to the power 1 by n to the power 1 by q xp, right? Now this happens for 1 less than equal to q less than infinity. Okay. So now the thing is, this is call this as way and call this as p. Okay. So the thing is, this happens for 1 less than equal to q less than b, but from a and b, q is infinity. So b boils down to a. So from a and b, we get what? We get this norm of xq is less than equal to n to the power 1 by q norm of xp, and this happens for 1 less than equal to p q infinity. Right? Okay, so this is true for any pq. So this shows that and p and q are arbitrary. So this that say that. So this implies this p norm on Rn is equivalent to q norm. Okay, so this is for 1 less than pq. So on Rn, so the LP norm is equivalent to LQ norm. Okay. So the thing is, okay, so okay, so we have done that. Any none. Now the thing is on Rn, actually the topology of Rn, I told you that that comes from L2 norm. So a little bit discussion. Let us do a little bit discussion. So Rn topology of Rn is really coming from L2 norm. It is L2 norm. Okay. And I told you that any LP is norm on Rn is equivalent to LP. So in particular, so they will really induce some topology. Okay. So we want to see that whether any norm on Rn is this equivalent to L2 norm. We saw that LP norms is equivalent to L2 norm. Okay. So now, okay, we will see later that any norm on Rn is equivalent to this L2 norm. So let us check that first. So let this be any norm on Rn. Okay. Now the thing is, so that really imply that norm x and u. Okay, so norm x is really so I is equal to 1 to n xi ei norm. So what is ei? Ei you know that this is really 1 0 0 sorry 0 0 0 0 0 0 0 0 and 1 in the ith position and rest are 0. This is 1 in the ith position. Okay, so that I can apply triangle inequality. So this will less than equal to I is equal to 1 to n norm of xi. And if I apply further this homogeneity, so this will be equal to I is equal to 1 to n. So module of xi and norm of ei. Okay, so this is any norm on Rn. So now this all this xi, okay, so this xi, so this is equal to really what I'm getting I is equal to 1 to n Now this coordinate xi is really, this modulus is less than equal to L to norm. So each coordinate modulus of each coordinate of x, that is mod of xi, is less than equal to L to norm. So I can really write this thing, I is equal to 1 to n, the norm of x2. So that will be implied norm of x less than equal to m into norm of where m is norm of u1. It's a norm of u1 plus norm of e2. So what I am getting, this norm of x is less than equal to m norm of x2. Okay, so okay. So I am getting this. Call this as say a. Now I have to prove to you that this, if I put in product of x, this is x minus y. From a, I will get this m of x minus y2. Now I have told you that now somewhere I have proved that norm of x minus y is less than equal to norm of x minus y. So okay, so this norm of x minus y I have proved before. So this is I have proved. So this is always greater than equal to norm of x minus norm y in the beginning, if I remember correctly. That's it. Norm of x minus norm of y modulus less than equal to a minus y. So I will get what? If I will that, so I will get this norm of x minus norm of y less than equal to norm of x minus y naught. Okay. And this is really n. So now in particular, so what I'm getting this norm of x minus norm of y is less than equal to m norm of x minus y to norm for all. Okay. Okay, so this is I'm getting, and this happens for all xy. This happens for all x comma y belongs to Rn. And call this B. So if fx is really norm x, from B it is clear that fx minus fy mod is less than equal to m into x minus, and call it C. So see that it says that this function. So C say that if this function fx is equal to norm x, it's continuous in the usual topology. Okay. So we have seen that norm x is continuous with respect to a topology induced from the norm first initially. Now I am saying that if you take any norm on Rn, so that is continuous with usual topology. So first conclusion, what we get? So conclusion, what conclusion? So wait, the function x going to norm x, and which I have written fx, is continuous with respect to the usual topology of Rn. Rn, and that topology is coming from where? To node. Topology of Rn, and that is coming from, this is Rn. So what is unit sphere on Rn? So S, okay, so unit sphere on is S01 with respect to 2 null unit. This is really x1 square plus this is nothing but this thing, x belongs to Rn. So that mod of x1 square plus mod of x2 square plus xn square is equal to 1, and this is nothing but Sn minus 1, right? Now the function fx is norm x is continuous on this thing, and this is Sn minus 1, and this is compact. Now the thing is, so and Sn minus 1, and we know that f is continuous on Rn, and this is compact. So we know that f is a positive, continuous one, strictly positive. Okay, so positive means strictly positive, because if it is a strictly positive continuous function on Sn minus 1, and since Sn minus 1 is compact, so as Sn minus 1 is compact, you know that in compact set, if something is a positive function, it's really, if something is a continuous function, it attains maximum and minimum as a compact. So there exists some C1 greater than 0 and C2 greater than 0. So that, and because the thing is positive, sorry, on compact set, a real valued function is always attains maximum and minimum. So that there is C1 greater than 0 and C2 greater than 0, so that f of W is less than equal to C1 and less than equal to C2 for all W belongs to Sn minus 1. Now let x0 not equal to x belongs to Rn. So that will imply that x by strict norm of x2. So this will belong to Sn minus 1. Or this is the unit sphere of the thing. So now what will happen? So this call, this is say D. So from D, it follows that. So this happens. F of this thing, x by norm x2. Okay. This is less than equal to some C1 and C2. So this will imply that, okay, C1, that what is the F, this is by definition, this is x by norm x2. Remember, this norm is homogeneous, so this color norm x2 will come out. So that will give you C1 less than equal to 1 by norm x2 norm x C2. So that will give you, and this happens for all x not equal to 0 in Rn. So this will give me these things. This will give me C1 norm x2 less than norm x less than C2x norm x2. This will happen for all x not equal to 0 not equal to 0 belongs to Rn. But this relation is really trivially true for all for 0, right? If x is 0, everything is 0. So this in particular, this relation will happen for all x. So look at this conclusion. What we get finally? We got what we got finally. We got that this norm, which was an arbitrary norm, this is equivalent to none. Okay. Okay. So finally, so this implies this is the thing. So what we have? So what we get, or let us call this lemma. So let this be a norm on Rn. So we got this lemma. So we have proved this lemma. So thus we have proved the following lemma. Following lemma. So what is the lemma? Let this be a norm on Rn. So then this norm is equivalent to L2 norm. Okay. Okay. So now theorem. Okay, so we want to prove a nice theorem. So on Rn, any two terms on Rn are equivalent. So proof is clear. Let norm A and norm B be two norms on Rn. So by previous lemma, norm A is equivalent to norm 2 and norm B is equivalent to norm 2. And by transitivity, so I have told you that norm A is equal to norm B is equal to norm C, the norm A is equal to norm C. So by transitivity, so norm A is equal to. So this proves our result. So what did we see? So we see that we saw that any norm, any two norms on so the thing is, so any on Rn, so that means on Rn there is a unit norm topology. So we can fix any norm on Rn and we can work with that norm. So if you are bothered about continuity, limit, and all kind of things, so nothing will change. Okay, so this is the first theorem we prove. Okay. Okay, so now on to something like that. So let B be a. So let us discuss a little bit. Let us discuss something. So discussion. So let B be a finite dimensional vector space. Yes. Suppose the dimension of B is n, and okay. Now you know that B is really isomorphic to Rn. So B isomorphic to Rn, and there is a linear isomer. So T is a linear isomer. Okay. So T is a linear isomorphism. Now the thing is, okay, suppose there is a norm, we have a norm on B. Okay, so suppose we have a norm on Rn. This is a norm on Rn. So using this linear isomorphism, I can define a norm on B. So what is the definition? So thus this norm on Rn will induce a norm on B while this thing. So this can be defined as like this thing, norm on B. Norm on B will be defined. Suppose here U is there, so I will define like this. This will cause, so I will define a norm on this thing. So norm of, sorry. So this will correspond to norm on B. So and what is the definition of norm B? So if U is there, so by definition I will define simply like T U, and this is the norm on R. Similarly, there is a norm on B, on B that will corresponds to norm on Rn. And what is that thing? Similar, so this will be defined like this. If X belongs to Rn, so that will given by definition T inverse X. So what it does say that? So norms on B, so this say that norms on B are really one-to-one correspondence with norms on Rn. And so norms on Rn are equivalent. So we know that, so norms on Rn are equivalent, and norms on Rn are one-to-one correspondence. So this implies that, so since norm on Rn are equivalent, this implies norm also on B are equivalent. So conclusion, any two norms on a finite dimensional vector space are equivalent. So we have any two norms on finite dimensional vector space are equivalent. It is indeed a Rn. So any finite dimensional vector space is nothing but Rn. Any finite non-linear space is nothing but Rn. So any two norms on finite dimensional vector space are equivalent. So we have proved this in testing result. Now the thing is, on Rn, any two norms are equivalent. So in particular, this any two on Rn, any norm is really equivalent to L2 norm, and L2 norm is complete. So you know that Rn is a complete matrix space. So that means so Rn is a complete matrix space. So any norm on Rn. So okay. So what I'm saying, on Rn, any two norms are equivalent. So in particular, any norm is equivalent to L2 norm, and the topology with respect to L2 norm or metric topology with respect to L2 norm is complete. So that means in any norm on Rn, okay, so the metric which will be induced from that norm will be complete. So in particular, Rn will be Banach space. And since any and that is really, that is also true for this finite dimensional vector space. So conclusion. So I am saying that conclusion. The thing is that any finite dimensional normal space non-normal space is a Banach space. Now one thing, okay, so this actually this is the end of the today's lecture. So I just wanted to tell you that I want to give you one or two questions to you. So the thing is, if here actually see that when you define LP norm, so there is a P in the right hand side. Okay, there's a P on the right hand side. So it makes sense to define LP norm like this. But look at the L infinite norm. So there is no infinity as such. So but we have defined an infinite norm like this. So there should be some region. Okay, why one call this quantity, why one calls this right hand quantity L infinity norm of X. So there should be some region. So we want to find that region. But I'm saying that if you when defining LP norm of X, so there is P in the right hand side. So it makes sense to index this by P. But the thing is, look at the right hand side. Okay. Here, there is no infinitive as such. So there should be some region to call this L infinitive. So you have to find out the region for defining this norm. So can the exercise is first. So why L infinite norm defined like that? Okay. And another thing, so you understand, and so next class actually you just go through the proof. The next lecture is before starting lecture, you just go through the proof how I have proved this. I have proved the result that two norms are equivalent. So you just assimilate the idea. So that will be needed probably in the future lectures. So with this, let me stop then, and so see you in the next lecture. Okay. Okay. Thank you.